Hi everyone. In the last video we talked about exponential notation, how useful it is to save time when writing out a lot of multiplication and just using an exponent instead. So we're going to kind of pick up where that video left off and just kind of quickly summarize what we saw in the last video. So we use 4 to the 5th instead of writing out 4 times 4 times 4 5 times, and that's what we call exponential form, using that exponent here instead of writing it all out in expanded form. So that's what we saw a little bit in the last video. We talked about how these can be written either form, given the other version. We talked about some vocab, and then we found a couple of rules. We're going to find some more laws or rules of exponents besides the first two that we found in the first video. What we saw so far in part A was that when we multiply with the same base, we just add the exponents, because really you're just counting how many of that base. So when there were 5 2's here total, it became 2 to the 5th. When there were 3 7's, 3 to the 7th, etc. And for these rules, you don't have to memorize them at all. If you're ever not sure, just write them all out. Write it in expanded form, rearrange things if needed, and just count how many pieces you have. That way you can get the right answer without having to memorize a million different rules. So that was our rule, though, for multiplying with the same base. Keep the base, add the exponents. For dividing, then, it's the opposite of what it was for multiplying. So when we're dividing, you keep the base and you subtract the exponents. Because essentially what happens is they cancel out. So like, for example, here 3 to the 5th divided by 3 squared would be 3 times itself 5 times, divided by 3 times itself twice. And what happens? Well, 1 3 on the top, 1 on the bottom cancel out a couple of times, and you're left with how many left? Well, I see 3 left, which is why it's 3 cubed. Okay, so that's why when we're dividing, we actually subtract the exponents, but don't forget to keep that base. We still need the base to stay the same. The other rules we've got here starting over here in part C. So we're going to again start with expanded form. We're going to take our exponential form, put it in expanded form, and look for a pattern. So 2 times 5 cubed. So what is that? Well, it's 2 times 5, 3 times. Now, this isn't very useful the way it's written, so we're going to rearrange things using our commutative property to put all the like pieces together. 2 times 2 times 2, and 5 times 5 times 5. The order never matters when it comes to multiplication or addition. Now we see, well, what do I have here? What we've got here is 2 multiplied by itself 3 times, and 5 multiplied by itself 3 times as well. So this becomes 2 cubed times 5 cubed. So our jump then is that this goes right to this. And we're going to see how that looks for other examples as well. So 5x squared would be 5x times 5x, which again, we can use the commutative property, rewrite this, 5 times 5, x times x. So that's 5 squared and x squared. So from here, we can jump right to here if we can figure out the pattern. For the next one, a lot more pieces here. 10xy squared times 10xy squared times 10xy squared, since there's 3 of them. Now rearranging would be 10 times 10 times 10 times x times x times x times y squared times y squared times y squared. Wow, okay. So now this is 10 cubed times x cubed. And now the y's here, well, this is y times y times y times y times y times y times, wait, too many y's, 6 y's. So y to the 6. So here we go. So it's 10 cubed, x cubed, y to the 6. So what ends up happening here with the exponents on the outside of parentheses is they actually go to each part on the inside of the parentheses when we are multiplying in here. Notice how there's no plus signs or subtraction signs. Everything is being multiplied inside, which is why we just take that exponent and give it to everything. But somehow we got a 6 there, so that's kind of interesting. So it was a 2, and now it's a 6. We'll see more of that pretty soon. But it looks like, again, we don't need the shortcut. We just wrote it out in expanded form and then just counted. So there we go. But what it looks like here is that we keep the bases the same. They just each get the exponent. So we have an exponent on the outside of parentheses. We keep the bases, but each get that exponent. Everything gets that power that was on the outside of the parentheses. So if it's ab to the m, a gets the m exponent, and so does b. They both get raised to that exponent of m, whatever it is. And again, we're going to see what happened with that 6. That was kind of weird. That y squared cubed became y to the 6. So that means that y squared cubed is y to the 6. There's a shortcut there too. Let's find out here in part D. So in part D, Mary's got an example. She said that 2 cubed squared is 2 cubed times 2 cubed, which then you can go from there to figure out a relationship. So we're going to try and use that for D number 1a. 3 squared squared. So we're going to use the outside exponent first. So that means 3 squared twice. Well, what does 3 squared mean? Well, that's 3 times 3. Same for that 3 squared. How many 3's are there? 4. See? Just lots of counting. So 2 and 2 somehow made 4. You can make a quick little guess to figure out what the relationship is, but don't go too far with it yet, because you want to make sure it works for more than just one example. So let's do 5 cubed cubed. So 5 cubed times 5 cubed times 5 cubed. So then we say, okay, well, that's 5 times 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 5. That's a lot of 5s. How many are there? 9 5s. So 3 and 3 make 9. Hopefully that's helping you figure out a pattern there. And then 2 squared to the 4th would be 2 times 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 2, which is 2 to the 8th. So our shortcut here, hopefully you see it by now, is that when we have power to a power, we multiply the exponent. So we keep the base and multiply the exponents. So for this one, it would be a to the mn, where m and n are being multiplied there. That's why back here we had y squared cubed is y to the 6, because you're really just multiplying. Groups of groups become just a multiplication. That's a nice another rule there, which is pretty cool. The last part here, part E, some kind of strange rules. So we're going to use what we've done before to kind of prove that these things are true. And proofs in math are kind of tricky to figure out how to do this. So let's see if we can figure this out. So a to the 0 is 1. So what that means is anything raised to the 0 power is 1, not 0, 1, which is kind of weird. People think it's 0, but it's actually 1. Let's see why that is. Well, what if I have 2 squared? Okay. What if I divide that by 2 squared? What should that be? Well, we've got a couple different ways we could write this. Anything divided by itself is 1. So this equals 1. Because anything divided by itself, 2 squared divided by 2 squared is 1. Okay. Well, now use your division rule. Our division rule said keep the base, subtract the exponents. So this is actually 2 to the 2 minus 2, which is 2 to the 0. And these are all equal. So 2 to the 0 equals 1. And then I just picked 2 just for, simplicity. It could be anything. It could be any exponents. So we could call it a to the anything, k, just to give it some letters, make it look more complicated, over a to the k, right? Those could be any numbers, so I'm using letters to show that. Well, that's 1, because, again, anything divided by itself is 1. That's a to the k minus k, which is a to the 0. So there you go. A to the 0 equals 1. So anything raised to the 0 is always going to be 1, which is super weird. Like, it could be anything crazy. 2xy squared to the 0, 1. Negative 4.2 pi x all to the 0 is 1, which is kind of crazy. But that is what the rule is saying here. Anything raised to the 0 power will always be 1. And then for this one, a negative 1 power, it's kind of interesting. Well, how do we get negative? So say you've got a to the 3rd divided by a to the 4th. Well, that would be a to the 3 minus 4 using our division rule, which is a to the negative 1. So that's how you get negatives. Okay, let's figure out why that's 1 over a. Well, that would be a times a up top over a times a times a times a on the bottom. And we can cancel out 1 with 1, top and bottom. And what's left? Well, there's only an a in the bottom. But what's left up top? You can't put a 0 here. People try and put a 0 there, but then the whole thing becomes 0, and that's not correct. We can't put a 0 there. What could I multiply these by without changing the value? Well, how about a 1? And there it is. That's why 1 over a equals a to the negative 1. That's a quick little example to show why that is. So we could do this for anything, though. Say it's x to the negative 2. That would be 1 over x squared. For the same reason as before. So how would you get that? Well, let's say if we do x divided by x cubed. That would be x to the negative 1, or x to the negative 2. Because it'd be x over x times x times x. So 1x cancels top and bottom. And you're left with 2 x's in the bottom. And a 1 up top. So basically what happens is any negative exponents are going to go to the bottom of the fraction and become positive. That's our last rule here. So this becomes, for our rule, 1 over a to the positive m. If you see a negative exponent, it flips to the other location. If it were already in the top, this is kind of or a bottom, I mean, say it was 1 over x to the negative 2, then that flips back up top, which is super crazy, but hopefully it kind of makes sense. Because if it was up top, it goes to the bottom, and then from the bottom, if it's negative, it goes to the top and becomes positive. That's kind of a tricky example. And those are all of our exponent laws or rules, and they're nicely summarized in this nice little chart here, which may or may not be useful to you. So hopefully if you're stuck, you can always just write it out and you can count from there. That's always a good suggestion. If you're not sure about the laws of exponents, just write them all out in expanded form, rearrange them if needed, and just use counting to find the exponential form.